Hi everyone, the channel Easy Lecture welcomes you. In this video we are going to discuss major formulas of electronics and communication engineering. So I have prepared these formulas. I have written these formulas while preparing for competitive exams, and here there are more than 450 formulas which covers major subjects from electronics and communication engineering. And these formulas are really helpful and needful to prepare for competitive exams like TRV Polytechnic exam, then junior engineer exam, junior telecom officer exam, and also for GATE exam. Hope you will like this video, and let us move on to this video. Here totally there are more than 450 formulas, and I have segregated these formulas into 50 numbers. So in each video we will be discussing 50 formulas. Okay. Before entering into the video, kindly subscribe my channel Easy Lecture. Now let us go for further discussion. Number 1, Q is equal to NE, where Q is total charge, N is number of charge carriers, E is charge of an electron, that is equal to 1.6 into 10 power minus 19 coulomb. So total charge is the product of number of charge carriers and charge of a single electron. Number 2, I is equal to Q by T, where I is current, Q is total charge, and T is the time. So we know the definition of current as flow of electrons or flow of free electrons, whereas there is another definition too, which is the current is also defined as the rate of change of charge. So here rate of change of charge, with that definition this formula comes. Next, V is equal to W by Q, where V is voltage, W is work done, and Q is the charge. Number 3, for 1 coulomb of charge, number of electrons required is the reciprocal of charge of single electron, that is 1 divided by 1.6 into 10 power minus 19, that is equal to 6.25 into 10 power 18 electrons. So for 1 coulomb of charge, number of electrons required equal to 6.25 into 10 power 18 electrons. Number 4, forbidden band of germanium at 0 Kelvin is 0.785 electron volt. Number 5, forbidden band of silicon is equal to, at 0 Kelvin equal to 1.21 electron volt. So forbidden band means the band gap between valence band and conduction band, and for germanium we have this much of energy gap between valence band and conduction band, and for silicon this is the band gap between valence band and conduction band. And 1 electron volt, number 6, 1 electron volt equal to 1.6 into 10 power minus 19 joule. So here joule, the unit of energy is joule. So 1 electron volt in energy equivalent, it is written as 1.6 into 10 power minus 19 joule. So for conductor, semiconductor, insulator, when we consider these materials, for conductors there is no band gap. Conduction band and valence band, they are overlapped with each other, whereas for semiconductors there is a small band gap, and the band gap is measured in electron volt. That means we have to give some energy, some force to take the electrons which are in the valence atoms, the valence electrons. We have to make the valence electrons as free electrons. We have to break the bonding of electrons between the bonding between the electrons and the atom, and we have to make them free. Only the free electrons constitute current. Okay, so in semiconductors some external force is required, some external energy is required to make free electrons, and the amount of energy required is with respect to this. For germanium, since it at 0 Kelvin it's electron volt, that is the forbidden band gap is 0.785 electron volt, which is less than 1 electron volt. The energy that we require to free electrons in germanium is less than 1.6 into 10 power minus 19 joule, whereas for silicon it is slightly greater than 1.6 into 10 power minus 19 joule. Whereas for insulator, the band gap energy is greater than 6 electron volt, so we need 6 times 1.6 into 10 power minus 19 joule of energy to liberate the electrons from the valence atoms, so valence shell. Okay, so which is not possible, and that is why we are unable to produce free electrons from these insulators, and the insulators, they do not conduct electricity. Now electrical neutrality law, Nd plus P is equal to Na plus N, where Nd is the donor concentration, P is the number of holes, Na is the acceptor concentration, number of acceptors, and N is the number of electrons. Number 8, so with this formula it is rewritten as Nd minus N is equal to Na minus P. Mass action law, product of electron and hole is equal to Ni square, where N is electron concentration, P is hole concentration, number of electrons, number of holes respectively. Ni is intrinsic carrier concentration. Then number 10, minority carriers is equal to Ni square divided by majority carriers. Number 11, minority carrier is equal to Ni square divided by doping. Then Fermi energy, Number 12, Fermi energy EF is equal to half mv square, where m is mass of an electron, that is equal to 9.11 into 10 power minus 31 kilogram. Number 13, V is equal to, so from this formula it is rewritten. Okay, so V is equal to Fermi energy half mv square means it is similar to kinetic energy, the formula of kinetic energy, and V is equal to root of 2 EF divided by m, right? Then Fermi direct function, number 14, Fermi direct function Fe for electron equal to 1 divided by 1 plus exponent of E minus EF by kT, where K is Boltzmann constant, it is equal to 1.38 into 10 power minus 23 meter square kilogram per second square per Kelvin, Boltzmann constant. Number 15, Fermi direct function for hole. So Fermi direct function for electron, this is for hole, it is equal to 1 minus Fermi direct function for electron. Next, thermal voltage, number 16, Vt is equal to Kt by Q, where Vt is the thermal voltage, K is the Boltzmann constant, T is the temperature, Q is the charge of an electron. K is equal to 1.38 into 10 power minus 23 joule per Kelvin. Here meter square kilogram per second square is rewritten as joule, it is represented as joule per Kelvin. So it is again Boltzmann constant. Number 17, Vt is equal to T divided by 11,600. Okay, substituting the value of K, Boltzmann constant, and Q, charge of an electron, we can write the formula as thermal voltage is equal to T divided by 11,600, and T is the temperature at room temperature, which is normally 300 Kelvin. Vt is equal to 26 millivolt. Okay, number 18, thermal voltage is equal to 26 millivolt at room temperature, which is 300 Kelvin or 27 degrees centigrade. Next, diffusion current. Number 19, diffusion current density due to electrons is equal to Q into capital Dn into dN by dx. Number 20, diffusion current density due to holes is equal to Jp comma diff equal to minus Q into dP into dP by dx. Number 21, total diffusion current density is equal to sum of diffusion current density due to electrons and diffusion current density due to holes. Number 22, current density comma J is equal to I by A. I is the current, A is area. Length of diffusion L is equal to root of D into tau, where D is the diffusion constant and tau is the carrier lifetime. Resistivity, number 23, R is equal to rho into L divided by A, where rho is resistivity and its unit is ohm meter. So this is resistance, R is resistance, rho is resistivity. This is the relationship between resistance and resistivity. Okay, next, conductivity. We know that the reciprocal of resistance is conductance. Similarly, the reciprocal of resistivity is conductivity. Conductivity comma sigma is equal to 1 by resistivity, that is 1 by rho. Number 25, sigma is equal to conductivity equal to carrier concentration into mobility into charge. Okay, conductivity due to electrons is equal to electron concentration N into charge of an electron Q into mobility of an electron mu N. Similarly, conductivity due to hole is equal to carrier the concentration of holes into charge of a hole into the mobility of a hole. Number 28, intrinsic, the conductivity due to intrinsic is N into Q into sum of the mobility of electron and hole, where N is the intrinsic concentration, Q is the charge of an electron or a hole, mu N is the mobility of electron, mu P is the mobility of hole. Then Ni is equal to 2 into N. Ni is the intrinsic concentration and 2N means N plus P. So N means number of electrons and P is number of holes, and at a equilibrium N equal to P, so 2N. Then number 30, mu N greater than mu P. So the mobility of electron is always greater than the mobility of hole. Number 31, mu is equal to V is D divided by epsilon, where Vd is drift velocity meter per second. In meter per second, epsilon is electric field in voltage per length, voltage per meter. Then unit of mobility mu equal to meter square per voltage second. 1 by mu is equal to 1 by mu 1 plus 1 by mu 2 plus 1 by mu 3, etc. Einstein equation E equal to mc square, so we know this already. Number 33, dN divided by mu n is equal to dP divided by mu p is equal to Vt thermal voltage, where dN and mu n are diffusion constant of electron and hole respectively. Vt is thermal voltage, it is equal to Kt by Q. We have seen this formula. And mu n and mu p are mobility of electrons and holes respectively. Now, for PN junction diode, number 34, width of depletion region, W is inversely proportional to root of doping. Number 35, barrier potential or cut-in voltage, comma V naught equal to Vt into logarithm of exponent of Na into Nd divided by Ni square, where Vt is thermal voltage and Na is the acceptor concentration, Nd is donor concentration, Ni is intrinsic concentration. Okay, Vt into natural logarithm of, so log E can be written as natural logarithm of Na into Nd divided by Ni square, where Na is acceptor concentration, Nd is donor concentration, Ni is intrinsic concentration. Next, number 36, cut-in voltage for germanium is 0.3 volt, or the voltage that is developed in barrier potential. Okay, then cut-in voltage or barrier potential of silicon is 0.7 volt. Number 38, width of depletion region, comma W is equal to root of 2 into epsilon divided by Q into open bracket 1 divided by Na plus 1 divided by Nd into V naught in meter, where W is width, epsilon is permittivity, Na is acceptor concentration, number of acceptors, Nd is donor concentration, number of donors, V naught is barrier potential. Next, number 39, capacitance, C is equal to epsilon into A divided by D. Number 40, capacitance is equal to C equal to dq by dV. Then number 41, at equilibrium, the diffusion current density and drift current density, they are equal. Number 42, diode forward current IF is equal to IS into exponent of Vd divided by eta Vt minus 1, where IS is reverse saturation current, Vd is cut-in voltage or barrier potential, eta is the recombination factor, and the recombination factor, sometimes the value may not be given in the question, but the material of a semiconductor used may be mentioned. So in that condition, if the value of recombination factor is not mentioned in the question, you can consider that the recombination factor value as 1 for germanium and 2 for silicon, and proceed the problem. Vt is thermal voltage, that is equal to Kt by Q, that is equal to 26 millivolt at 300 Kelvin. So we know this already, we have seen this. Next, Zener breakdown. Electric field EF is inversely proportional to W, width of barrier potential. Doping is inverse, root of doping is inversely proportional to width. We have seen this already. Then as doping increases, what happens? Since inverse relationship is there between width and doping, width decreases, and here direct relationship is there between electric field and doping. So electric field increases. As doping decreases, electric field also decreases, but width increases. Number 45, static resistance R is equal to V by I in ohms. So it is the ratio of voltage and current, whereas static conductance, G is reciprocal of resistance, and that is the ratio of current to voltage, I divided by V. Number 47, dynamic resistance, small r is equal to differentiation of voltage with respect to current, dV by di, that is equal to eta into Vt divided by If, where eta is the recombination factor, Vt is the thermal voltage, and If is the forward current. Number 48, dynamic conductance is the reciprocal of dynamic resistance, that is equal to 1 by R, that is equal to differentiation of current with respect to voltage, that is equal to If divided by eta into Vt, where eta is the recombination factor, Vt is the thermal voltage, and If is forward current. Next, diode capacitance. Number 49, transition capacitance for reverse biasing, Ct is equal to epsilon into A divided by W. Number 50, Ct is directly proportional to root of doping. We know that width is inversely proportional to root of doping, whereas this transition capacitance is directly proportional to root of doping. So with this, we shall wind up this video. So this is the first segment of major formulas that may be that is highly essential to be prepared for a competitive examination. Meet you again with another segment, that is formula numbers from 51 to 100. We shall be discussing another video in the next video. So if you like this video, kindly comment, and don't forget to subscribe my channel Easy Lecture, and kindly share this video. Meet you again in another video. Until then, bye. Thank you.